Welcome to our talk on fine-grained stop-move detection in UWB-based trajectories. Localization systems like GPS today provide a wealth of trajectory information that can be used to extract higher-level mobility patterns, like, for instance, where the localization target stops and when it resumes moving. So this has been applied in applications like animal migration or the movement of people in urban settings, but with time constants that go from hours to months and distances between tens of meters to kilometers due to the application, but also as a function of the fact that GPS has an accuracy of only meters. Now, new technologies like ultra-wideband provide accuracy of centimeters, yet the question of what we can achieve in this case with respect to mobility patterns like stop-move detection is still an open one because this aspect is still largely unexplored. So what can we do with fine-grained stop-move detection? Let me give you an example. So for instance, imagine a person that is visiting a museum and reaches a particular exhibit, stays there for a little while, and then moves to an exhibit nearby that maybe is only 50 centimeters away. So can we actually accurately detect these fine-grained stops with ultra-wideband? And the positive answer actually is relevant not just to museum, but to many other applications like retail, logistics, and so on. So the goal for our work is the one that you see here, which entails having ultra-wideband trajectories that are not as widespread in the literature like GPS ones, and therefore we gathered in a real-world setting. Then we applied existing techniques, reference ones from the literature, to see how well they perform, which is a challenge per se because that requires a quantitative way to compare them. And in the literature, there is not a well-accepted quality metric to this goal. So a part of the contribution is actually to define one that then allowed us to compare these techniques on quantitative grounds and in terms of their spatio-temporal accuracy with stops very near in time and space, so fine-grained stop-move detection, as I mentioned before. We did it in a real-world experimental setup in a Natural Science Museum in Trento, in Italy, also known as MUSE, where we installed an ultra-wideband localization system, a time difference of arrival system to be precise, as a permanent infrastructure. We gave people tags by which we can track their movement as they go around in the museum. In the museum, we defined 45 points of interest where visitors should stop so that we have a controlled ground truth. The position and the duration for each stop is actually acquired very accurately using cameras, laser meters, and the specialized application. And overall, we have 209 stops in the 9 trajectory that we collected for a total of 70,000 ultra-wideband positions. Now, this point of interest, these stops, are very close to each other. They are below 1 meter, and they're also very short in time. On average is about 12 seconds. And then we disregard those that are below 10 seconds because for this particular application is deemed irrelevant, although we kept it configurable in our scenario. So in essence, our dataset is made of ground truth stops that are very close in space and very short in time. So they are very fine-grained, which is our goal. Then we also ascertained the error that is given by the ultra-wideband positioning per se, which we verified is sub-meter. On average is about 46 centimeters, which is significantly better than Bluetooth or Wi-Fi, that are technologies that are used for the same kind of applications, but that have errors that are of the order of meters. So this is an example of the trajectory we collected in our experiments. As you can see, the white dots are the raw position that are output by the ultra-wideband localization, and they are affected by significant noise, which is why we also apply Kalman filter to them by obtaining the trajectory that you see in gray, which is significantly smoother. The difference in the input trajectory may make a difference in the actual quality of the stop-move detection, which is why we collect both. Then you also see the colored points. Those are the positions that actually fall into the true stop time duration. So the one that we verified with ground truth. And you can see the sequence of colors with the numbers, which basically represents the trajectory that is followed by the visitor inside the museum. Now, what do segmentation technique do? Well, they take as input one of the trajectories as a sequence of units, as we call it, so pairs, position, timestamp, and then they try to estimate the stop duration without ground truth, of course, and the stop position, which is taken as the centroid of the points that fall into the stop duration. Now, the details of each technique you can find in the paper, but we compare three that are representatives and that are based on very different concepts like distance, density-based clustering similar to dbScan, and velocity, which we actually take directly from the Kalman filters that are used for tracking. So they're basically at zero cost, so to speak. The key point, however, as already mentioned, is how to actually compare these techniques, not only against each other, but also against different configurations on the cells in order to find the best one. Now, we do have ground truth as a baseline, but we lack a notion of quality of stop move detection, which is not present in the literature. And we also have a fine spatial temporal resolution, which demands a novel approach, which basically brings us to our contribution that is a stop-centric metric. Here you have an illustration of the ground truth duration intervals in green and the estimated ones that are in red. What our metric does is two things. First, tries to match the estimated to the ground truth ones based on those that are closer in temporal overlapping. Again, details are in the paper, but this is cast as an optimization problem that allows us to do this optimal matching, which in turn allows us to reuse well-known concepts of true positives, false positives, and negatives, precision and recall, and especially the concise indicator called F-score that basically is a very concise way to characterize the quality of this matching. But then this is not enough, because I could have a situation in which two stops are matched, but one is significantly shorter than the other. And so to quantify how similar the duration of the stops are, we use a second metric, which is based on the Jacquard index, which characterizes precisely this similarity. Now, this metric that, as we defined, is very expressive because not only it allows us to match and quantify, but also to determine the type of false detection. So like in this case, for instance, you can see that the D4 has been estimated and merges two ground truth stops, G2 and G3. Similarly, in this case, G4, that was the ground truth, was split in three. Well, these kind of things that I'm showing you visually can actually be derived based on our metric, providing further insights into the quality. Now, how many true stops are actually found? Overall, in our dataset, there are 199 to discover. And you see here that in the column TP, that stands for true positive, the vast majority of them are actually found by whatever combination. Remember, we have three techniques, and then we have two different data sets, one with raw and one with filtered points. And this latter aspect is actually important because, as expected, smoothing trajectories with Kalman filters improves detection quality, which, however, remains still pretty high. The other interesting thing that we show here is that different techniques have different drawbacks. For instance, SPD tends to suffer more from split stops or short stops, while 6CAN tends to suffer more from merged stops. And knowing these different drawbacks is actually relevant with respect to the application requirements to be able to choose the technique that is most appropriate. In general, however, 6CAN in the configuration that we tested is the one that provides the best performance according to the metrics that we define for ourselves. What are the sources of error in stop position? We start with the ground truth stop position, which is the green dot that you see there, for instance, at the edge of a table of the museum. Well, even if you know precisely the stop duration, which we do in our ground truth data set, the associated centroid that is obtained by taking all the points that fall into this duration already has an error. The error is intrinsic in the localization system that we use, which is ultra-wideband. As we said, it's better than others, but still is significant. Then, in addition to that, you have the fact that you don't have normally ground truth stop duration. You have an estimated one by the various techniques that we considered. And for instance, if it's shorter, like in this case, the centroid, the red one in this case, is slightly to the left, which induces an additional error. So the actual complete error in stop position is given by the combination of the two, and is the error shown in number 3 in the picture. So what is the actual magnitude of this error? Now, interestingly, the second one, so the one that can be ascribed to the stop move technique, is actually rather small, because the error on the duration is on the order of a few seconds, which translates in a small error of only 3 to 6 centimeters in the stop position. Instead, the errors in terms of position are dominated by ultra-wideband localization, which, as we have seen before, are on average 46 centimeters. Yet the interesting thing is that even without ground truth, these techniques can still enable a correct association of the stop to the closest point of interest. As you can see on the right, all of them get more than 90% the correct association in the case of the true positives that are found by the technique itself. And of course, there can be also false positives. So even if you consider everything, you're still above 80%, with 6CAN performing the best, in the best case, at nearly 89%. And remember, all of this is actually achieved with point of interests that are within decimeters and stops that can be as short as 10 seconds. To conclude, we started from the premise that ultra-wideband-based fine-grained stop-move detection has not been explored quantitatively. Therefore, first of all, we contributed a novel metric that allows us to characterize the quality of stop-move detection. And then we used it to compare existing techniques based on ultra-wideband trajectories that have been gathered in a real setting. We found out that these existing techniques that were originally developed for GPS are actually directly applicable to ultra-wideband. And also, they are not the main source of error, which raises the question of how can we do better? Novel stop-move techniques can be provided, but at the moment, the actual quality is limited by ultra-wideband position, which is currently limited by the characteristic of the technology, which is ever improving, and also by aspects like body shielding that are currently the subject of active research. Finally, our results are immediately useful, but they are gathered in a control setup in order to have reliable ground truth to perform the comparison. Yet we believe that these are the stepping stone that allows us to push the envelope of mobility pattern analysis in novel ultra-wideband applications by showing what can be done with fine-grained stop-move detection. We basically pave the way for applications that exploit these in the real world, in not only in the museum scenario, but in several other applications. Thank you very much for your attention.